Hello everyone, I'm Hanisha Manohar, here to present my Tech Talk presentation for the course operating systems. The topic I selected for my presentation is virtual memory. Let's begin. Let's get on with the basic introduction on virtual memory. Virtual memory is the memory management technique that allows the operating system to extend the available RAM by using a portion of hard disk. This enables the system to run larger programs and facilitate multitasking by swapping data between RAM and disk. Virtual memory plays a crucial role in modern operating systems to optimize memory usage and improve system performance. So basically, virtual memory is a storage allocation scheme in which secondary memory can be addressed as though it wasn't the part of the main memory. It assumes it was a part of main memory and it can be addressed. The addresses a program may be used may use to reference memory are distinguished from the addresses the memory system uses to identify physical storage sites, and program generated addresses are translated automatically to the corresponding machine address. So let's discuss how virtual memory works. When a program is running, the OS divides its memory into fixed size blocks called pages. Pages that are not currently in use are swapped out of the hard disk, freeing up space in RAM for other tasks. When the program needs the data from the swapped out page, the OS swaps it back to the RAM, allowing the program to continue its execution. So basically, a memory hierarchy consisting of computer's system memory and disk that enables a process to operate with only some portions of its address space in memory. Virtual memory is what its name indicates. It's an illusion of a memory that is larger than the real memory. We refer to a software component of virtual memory as a virtual memory manager. The basis of virtual memory is non-contiguous memory allocation model. The virtual memory manager removes some components from memory to make room for other components. Benefits of virtual memory. Virtual memory allows for efficient utilization of physical memory resources. It enables the system to run programs that are larger than the available physical RAM. Virtual memory also facilitates multitasking by providing each program its illusion of having its own contiguous memory space. The size of virtual memory storage is limited by the addressing scheme of the computer system and the amount of secondary memory available, not by the actual number of the main storage locations. It is a technique that is implemented using both hardware and software. It maps memory addresses used by program called virtual address into the physical addresses in a computer memory. Page faults. A page fault occurs when a program tries to access a page that is not currently in the RAM. The OS then retrieves the required page from the disk and swaps it into the RAM, causing a temporary delay in the program execution. Minimizing page faults is crucial for optimizing system performance and reducing latency. So there's a process called demand paging. The process of loading the page into memory on demand whenever a page fault occurs. This process is known as demand paging. So basically, all memory references within a process are logical addresses that are dynamically translated into physical addresses at runtime. This means that a process can be swapped in or swapped out of the main memory, such that it occupies different places in the main memory at different times during the course of execution. A process may be broken into a number of pieces, and these pieces need to be continuously located in the main memory during execution. The combination of dynamic runtime and addresses, translation, and the use of page or segment table permits this. If these characteristics are present, then it's not necessary for that all the pages or segments are present in the main memory during execution. This means that the required pages need to be loaded into the memory whenever required. Virtual memory is implemented during demand paging or demand segmentation. Let's differentiate between paging and swapping. Paging involves dividing the virtual memory into fixed size pages, while swapping involves this moving entire processes between RAM and disk. Paging is more efficient as it allows the operating system to manage memory on a granular level. Swapping is used when there is need to free up a large chunk of memory quickly. Let's get on to the differentiation more deeply. Swapping is a mechanism in which a process can be swapped temporarily from secondary storage and it as paging proves which what use in swapping and secondary memory. Paging equal size memory blocks or pages move between the main memory. Let's swapping is less flexible, page is more flexible. In swapping, there are more processes in the main memory. In paging, there are fewer processes in the main memory. In swapping, it's suitable for heavy workloads. Paging is suitable for small and medium workloads. Swapping helps CPU to access processes faster, whereas paging helps to implement virtual memory. Demand paging. Demand paging is a technique where the operating system only loads pages into RAM where they are actually needed by the program. This helps to reduce unnecessary disks, input output, and improves overall performance. Demand paging is a key feature of virtual memory systems to minimize memory wastage. So basically, demand paging system loads only pages only on demand, not in advance. Instead of swapping the entire process into memory, the pages or the lane sweeper is used. A lane sweeper brings only the necessary pages into the memory. So let's see what is demand paging. Let's see the process of demand paging includes the following steps. The steps in which the process of demand paging uses. If the CPU tries to refer the page that is currently not available in the main memory, it generates an interrupt indicating the memory access fault. Then the operating system puts the interrupted process in a blocking state. For the execution to proceed, the operating system must bring the required page into the memory. The operating system will search for the required page in the logical address space. The required page will be brought from the logical address space to physical address space. The page replacement algorithms are used for decision making of replacing page in the physical address space. The page table will be updated accordingly. The signal will be sent to the CPU to continue the program execution and it will place the process back into the ready state. Hence, whenever page fault occurs, these steps are followed by the operating system and required page is brought into the memory. Memory mapping. Memory mapping is a process of mapping virtual addresses to physical addresses in memory. The OS maintains a date table that keeps track of mapping between virtual and physical memory addresses. Memory mapping allows programs to access data stored in virtual memory transparently. There are two kinds of addresses in virtual memory. CPU uses virtual address and memory uses physical address. Hardware translates virtual address to physical address by an operating system managed table, the page map. Here is a depiction diagram which shows how a memory management unit uses virtual memory in order to execute processes and tasks. TLB, translation leukocyte buffer. The TLB is a cache that stores recent translations of virtual memory addresses to physical addresses. By catching these translations, the TLB helps to reduce the overhead of memory mapping and speeds of memory access. TLB misses can lead to additional latency or the system needs to consult the page table for translation. Working set model. The working set model is a concept that defines the set of pages that a program actively uses. during its execution. By keeping the working set in RAM, the operating system can minimize page faults and improve program performance. Monitoring and managing the working set size is crucial for efficient memory management in the virtual memory systems. So the working set model, Peter Denning defined the working set of a program as a way to model the dynamic locality of a program in execution. Definition includes WS, T of W. The pages is P. I was referenced in interval T to T minus W, where T is the time, W is the working set window, backward looking interval. So a page is in the WS only if it was referenced to the last W references. Memory overcommitment. Memory overcommitment is a strategy where the OS allows programs to allocate available. This can lead to potential performance issues. The system runs out of physical memory and relies heavily on swapping. Balancing memory overcommitment with system resources is essential for maintaining optimal performance. Memory compression. Memory compression is a technique used to reduce the need for swapping by compressing pages in RAM. Compressed pages takes up less space, allowing the system to store more data. Memory compression can help improve system responsiveness and reduce the impact of memory compression. Here in the diagram, as you can see, the data before memory compression, the active data. After memory compression, the data is not specified, is sliced into inactive, active, and free base. So the inactive data is stored in one, active data in free space. So memory compression actually helps to optimize the RAM and to make the processing faster. Swap space. Swap space is a dedicated portion of the hard disk reserved for storing swapped out pages in the RAM. Having sufficient swap space is crucial for virtual memory systems to handle memory overflow and prevent crashes. Properly configuring swap space sizes based on system requirements is essential for optimal performance. Swap space therefore resides in normal file system and separate disk partition. Memory management unit. The MMU or the memory management unit is a hardware component that translates virtual address to physical address. It plays a crucial role in implementing virtual memory by enforcing memory protection and managing memory access permissions. The MMUs are integrated to modern processors to support virtual memory operations efficiently. Memory fragmentation. Memory fragmentation occurs when the available memory becomes fragmented into small, non-contiguous blocks. Fragmentation can lead to inefficient memory allocation and increased overhead in managing memory. Defragmentation techniques can help optimize memory usage and reduce the impact of fragmentation on system performance. As memory is allocated and delocated, fragmentation occurs. External and internal. In external, enough space exists to launch program, but it's not contiguous. In internal, allocate more memory than asked for to avoid having small holes. Memory leak. A memory leak is programming error where a program fails to release memory after it's no longer needed. Memory leaks can lead to gradual depletion of available memory, resulting in system slowdowns and crashes. Detecting and fixing the memory leak is essential for ensuring stable and reliable software performance. Let's discuss security implications in virtual memory. Virtual memory introduces new security challenges such as page table manipulation and memory disclosure vulnerabilities. Memory isolation mechanisms are crucial for protecting sensitive data from unauthorized access in virtual memory systems. Address space layout randomization (ASLR) and memory protection techniques help mitigate security risks in virtual memory environments. Let's discuss the future trends in virtual memory. Future advancements in virtual memory may focus on improving memory compression algorithms, and reducing memory latency. Technologies like non-viable, non-volatile memory and persistent memory may revolutionize virtual memory systems by providing faster storage options. Memory learning algorithms could be utilized to optimize memory management strategies and enhance system performance in virtual memory environments. Now let's discuss few advantages in virtual memory. One of the main advantages of virtual memory is more processes may be maintained in the main memory. Because we are going to load only some of the pages of any particular process, there is room for more processes. This intense, this otherwise leads to more efficient utilization of the other advantage of virtual memory is a process may be larger than all of the main memory. One of the most fundamental restrictions in programming is lifted. A process larger than the main memory can be executed because of the demand paging. The operating system itself loads pages of process in the main memory as required. It allows greater multi-programming levels by using less of the available memory of each process. It has twice the capability of addresses as the main memory. It makes it possible to run more applications at once. Users are spared from having to add memory modules when RAM space runs out, and applications are liberated from shared memory management. When only a portion of program is required for execution, speed has increased. Memory isolation has increased security. It makes it possible for several larger programs or applications to run at once. Memory allocation is comparatively cheap. Doesn't require outside fragmentation. It is efficient to manage logical partition workloads using the CPU. Automatic data movement is possible in virtual memory. Here are the advantages. So now let's discuss the disadvantages of virtual memory, which are very few in nature. One of the disadvantages includes it can slow down the system performance as data needs to be constantly transferred between the physical memory and the hard disk. Second one is it can increase the risk of data loss or corruption as data can be lost if the hard disk fails or if there is power outage while the data is being transferred from one hard disk to the physical memory or two or four otherwise. The third disadvantage is it can increase the complexity of memory of the memory management system as the system needs to be needs to manage both physical and virtual memory. There's a small topic in virtual memory called page fault service time. It's basically the time taken to service the page fault is called page fault service time. There are actually totally 6 steps to uh, perform all the page fault service time. Now let's discuss a few case studies actually related to virtual memory. One case study is Windows virtual memory. Windows uses a paging file on the hard disk to extend the available virtual memory. The size and configuration of paging file can be adjusted based on system requirements and usage patterns. Windows also supports memory compression and prefetching techniques to enhance virtual memory performance. Let's see the case study where Linux uses swap space. Linux uses swap space as a mechanism for extending virtual memory beyond physical RAM. Administrators can configure multiple swap of partitions or swap files to accommodate varying memory demands. Linux kernel parameters allows fine-tuning of swap space usage and behavior for optimal performance. Before the conclusion of the virtual memory. Virtual memory is a crucial component of modern operating systems that enables efficient memory management and multitasking techniques. By extending RAM with storage, virtual memory allows systems to run larger programs and handle multiple tasks simultaneously. Understanding the principles and best practices of virtual memory management is essential for optimizing system performance and ensuring seamless user experience. Let's discuss some frequently asked questions in virtual memory. One frequently asked question is How does virtual memory work? Virtual memory works by dividing the virtual address space used by the program into smaller units called pages. The operating system manages a mapping between the virtual addresses used by the program and the physical addresses in the actual RAM or the disk. When a program accesses a virtual address that is not currently in the physical memory, a page fault occurs. The operating system then retrieves the required page in the disk and brings it to the RAM, repeating other pages with the same. This is how a virtual memory works. The question, frequently asked question is what are the benefits of the virtual memory? Virtual memory provides many benefits, such as increased memory capacity, memory isolation, simplified memory management, improved system stability, etc. So, as we have come to the end of the presentation, hope you got the briefing of how virtual memory works. Thank you for your time. Have a good day. Thank you very much.